Yes, welcome back. We are looking now at the structure of the spongy bones. Spongy bones will have a similar structure to the compact bone, with one major difference is the arrangement of the lamellae, osteocytes, and canaliculi. So we've got everything, but we don't have this arrangement of osteons. So we don't have this typical structure of the osteon. Instead, we have irregularly arranged lamellae, as you see on here, but everything else is going to be located inside those irregularly arranged lamellae that contains the osteocytes, canaliculi the same way like I do have in the compact bone. Looking at the chemical composition of the bone contains an organic part and an inorganic part. The organic part includes the cells, which are my osteogenic cell, my osteoblasts, osteocytes, and osteoclasts, as well as the osteoid. And the osteoid is the organic bone matrix that will be secreted by the osteoblast that has the ability to become calcified. If you remember when we discussed the osteoblast, we mentioned that is going to be responsible to produce the osteoid, this protein that has the ability to get attached to the calcium. So the protein part on here is going to be considered as a major part of the organic structure of the bone. The inorganic part is going to be the minerals that are attached to the osteoid, and this includes the calcium and the phosphorus. For the in-class activity, can you answer this question here, number 9, for today's in-class activity? What do we call the end of a long bone? If you remember, a long bone is going to be formed of a proximal bulging part, a distal bulging part, and those two are connected by a shaft. So what do we call those bulging parts on here? What do we call the bulging parts? Go back in here. This is my epiphysis. Epiphysis. So again, we call those ends are the epiphyses of my long bone. So the good answer here is going to be C. Moving on to the bone development or osteogenesis or ossification, the bone tissue formation. This takes place in 3 stages. First, I have the bone formation that begins by the 2nd month of development. Then we've got the postnatal bone growth, which is going to be taking place until early adulthood. And the third is going to be the bone remodeling and repair. And this is a lifelong process. So whenever I have a fracture, I have the ability to repair the bones. This is a lifelong process that allows me to remodel, repair the bone. Moving first to the ossification or the bone formations that takes place prenatally, starting from the 2nd month of development. We have 2 types of ossification. We have the intramembranous ossification and the endochondral ossification. Intramembranous ossification, I'm starting with a connective tissue membrane, a fibrous membrane, that will be responsible for the formation of the flat bones. This includes the clavicle and the cranial bones. So We're looking here at the intramembranous ossification. I start with a connective tissue membrane, fibrous membrane. So I have fibroblasts, I have collagen fibers. And at the center of the membrane, I will have a cluster of osteoprogenitor or osteogenic cells that will differentiate into osteoblasts, and the osteoblasts will start to form their osteoid, and the osteoid will become calcified. This osteoid that I am forming is getting its blood supply through blood vessels that are embedded within the membrane. I cannot simply break down those capillaries, those blood vessels. So what I'm doing here is I'm avoiding them and building my trabecularly around the already existing blood vessels. And this is why I have this irregular form of the trabecularly, which gonna become the spongy bone forming the internal core of my flat bone. As I keep moving to the outside of the membrane, I have less blood vessels. So now the osteoblasts will have the ability to build up those osteons. So I have more space to the outside, away from the blood vessels. I'm not trying to avoid the blood vessels as I did at the center of the membrane. So I will be capable to build up those regular patterns of the compact bone, which are my osteons. So I'm building up the osteons to the outside of the bone. So this is why a flat bone gonna have an internal core formed of spongy bone, and on the outside of the spongy bone on both sides, you've got the compact bone. So again, what do we call this ossification? It's my intramembranous ossification, and this is the type of ossifications that I have in my flat bones. Again, I started by a fibrous membrane. I form the ossification center in this membrane, and I will start to build up my bones starting from the center, going to the peripheral parts. That's why we're gonna have fontanelles. What are the fontanelles? Those are the soft spots in the skull of the baby after birth. Why? Because this was a membrane, this was another membrane. I started the ossification from the center of each of those membranes. So by the time of birth, I wouldn't have completed the ossification of all the membranes. So I have those parts that are still not ossified in the peripheral ends of the membrane. And those are what we call the fontanelles, the soft spots in the head, on the head of the baby. Did you ever feel the soft spots on the head of a baby? Yes. What are those soft spots? Those are simply parts of the membrane that haven't been calcified yet, because you start at the center and you go peripherally, like this. The other type of ossification is called my endochondral ossification from the name on here. Endo means inside, and chondro means cartilage. This ossification relies on cartilage, and this cartilage it's going to be calcified and transformed into bone. So I did have a small form of the bone like this, which is formed of cartilage. This hyaline cartilage that is forming my primary form of the bone is going to be invaded by a blood vessel at the center of the shaft of the long bone. And this is where I've got the primary ossification center, the same exact concept. What will I do? I would start to form my osteoblasts that will build up my osteoid. And again, I started to form small trabeculae, but because the shaft gonna be preoccupied by a large vessel on the inside to deliver the nutrients and oxygen needed for those cells to proliferate and to build up the bone, the osteocytes the osteoblasts avoiding those large vessels in the center of the shaft of the bone, they will be forming the bone on the outside. And as they are not trying to avoid the blood vessel anymore, because they are actually forming the bone around the blood vessel instead of around multiple small vessels like what we've seen in the intramembranous ossification, I will be able to form compact bone on the outside, but the inside that is preoccupied by this large vessel will become the cavity. We call this is my medullary cavity. How about the epiphyses? Epiphyses will start to form at their centers secondary ossification centers. And the secondary ossification centers are getting blood supply through tiny vessels, the same way like I did have in my intramembranous ossification. So you've got tiny little vessels that will be given the blood supply needed for the growing bone to be formed. As you see on here, I will be trying to avoid those tiny little vessels building up irregular patterns of trabeculae. But as I move away from those tiny vessels, I will be able to build up compact bone on the outside. So I have spongy bone on the inside because I'm trying to avoid those little vessels. And as I move away from the vessels, I will be able to form my osteomes, building up my compact bone layer. Something that we need to be aware of, that the cartilage doesn't tolerate calcium. So once you add calcium, the cartilage will be destroyed. So what I'm doing here is a replacement of the cartilage by bone. And as I add osteoid, it becomes calcified, and this will cause the degeneration of my cartilage. During childhood, I do not complete the ossification of the cartilage. I would still have a plate of cartilage between the epiphyses and the diaphyses. We call this here is my epiphyseal plate. Epiphyseal plate is the cartilage that's going to be remaining between the epiphyses and the diaphyses. Why do you need this plate? Because something that we need to be aware of is that you can't build up bone from scratch. I can't build up bone from nothing. I need to have cartilage first to form my framework and then replace the cartilage with bone. So to grow my long bones in length, what will I need to do? I need to keep a cartilage plate that will be growing and then will be replaced by bone. So if we're looking here at the junction between the bone and the cartilage, so I see here hyaline cartilage normally, but what is a very obvious characteristic here is that the cells are rapidly proliferating. So you see many cells that are located next to one another. Those cells are rapidly dividing. We call this zone in the cartilage is my proliferation zone. This is where the cells, the chondrocytes, are rapidly proliferating. As those chondrocytes become older, you will see that the cartilage cells are becoming larger in size. They will become mature cells. And those large cells here, we call the zone that they are occupy, it's my hypertrophic zone. This is where I have the exponential growth of the chondrocytes. Underneath it, I have the zone where I will start to add calcium along with my osteoid from the growing bone. And as I calcify the cartilage cells will start to die. And the matrix will start to deteriorate. So as you add bone to the cartilage, as you add calcium to the cartilage will start to deteriorate. And now you've got bone that is not remodeled. So I've got irregular pattern of the bone. This bone tissues that I've added needs to be modified into its final shape, and this takes us to the next zone, which is my ossification zone, where the new bone is going to be formed. So if we're looking here at the junction between the cartilage and the bone, we're going to see 4 zones. First, the one that shows the rapid proliferation of the chondrocytes, the rapid enlargement of the cartilage plate. This is my proliferation zone. Then the cartilage become mature, the cells will become larger in size. This is called my hypertrophic zone. The third zone where I'm adding calcium to deteriorate and destroy the cartilage. This is my calcification zone. And finally, I will be modifying this cartilage into the final shape of the bone. This is my ossification zone or my osteogenic zone. What do you think? Can you grow your long bones in length right now? Can you become taller right now? Yes, they will be growing towards both sides, but mainly towards the proximal epiphysis. So distal epiphysis is going to disappear early in life compared to the proximal epiphysis. So what do you think? Can you become taller? Can you grow your long bones in length right now? No. Why? Because simply you don't have any more of the epiphyseal plate. So this is my proximal epiphysis. This is my diaphysis, like this. And in between, we've got the epiphyseal plate, which is formed of hyaline cartilage. Let's say during childhood, I was growing my cartilage 1 centimeter, and my bone replaces this centimeter. So let's say on here, if I'm separating this cartilage, this was the epiphyseal plate thickness that I'm born with. I will add 1 centimeter each year, and then 1 centimeter of the cartilage gonna be replaced by bone. So what happens to my long bone? It grows 1 centimeter this year. Next year, what will I do? Add 1 centimeter, and I replace 1 centimeter. So the epiphyseal plate is kept almost constant. So I started by having 2 centimeters of cartilage. I still have those 2 centimeters of cartilage, but I've added to them 2 centimeters of bone over the last 2 years. But what happens during puberty? During puberty, I have a sudden rise of the sex hormones. Sex hormones are going to be stimulating the cartilage proliferation and the bone formation. It's going to be stimulating both of them. But it stimulates the bone formation at a higher rate compared to the cartilage formation. What this means, so let's say you were adding 1 centimeter each year to your cartilage. Now, under this sudden surge in the secretion of the sex hormones, you're going to be adding 2 centimeters of cartilage. And instead of replacing 1 centimeter of cartilage by bone, you're going to be replacing instead 3 centimeters. So you see on here, I'm adding 2 centimeters of cartilage, but I'm replacing 3 centimeters rather than 2 centimeters. So the bone formation is going to be at a faster rate compared to the new cartilage formation. So what will I end up with? I did have 2 centimeters. So how many centimeters of cartilage do I have right now? 2 plus 2 is 4. I replace how many this year? I replace 3. So 3 of them gonna be replaced. So what is the amount, what is the thickness of the cartilage that I still have by the end of the year? I did have 4. I replaced 3 of them, so I still have 1. So I have 1 centimeter of cartilage that remains. Still under the effect of the high levels of sex hormones, I will be adding 2 centimeters of cartilage. So now I have 3 centimeters total, but I'm also stimulating the bone formation. So the bone gonna be replacing 3 centimeters of the cartilage. So what will I end up with? I will end up with having no further cartilage that is remaining. So can I grow my bone in length, my long bones in length anymore? No. So all the cartilage has been replaced. And this explains why during puberty, you will see the children are growing fast, and then they stop getting taller. Why this happens? Because sex hormones are going to be stimulating the cartilage formation and the bone formation. But again, which one at a faster rate? Bone formation. Bone formation is taking place at a much faster rate compared to the cartilage formation, and this what will cause the fusion of the epiphysis to the diaphysis and the disappearance of the epiphyseal plates. This is how long bones are growing in length, but how would they grow in width? So what we're going to be doing here is this is my medullary cavity, and this is my bone. We'll keep adding bone layers to the outside, but in the same time, I will be breaking down bone from inside, like this. So I'm adding bone layer to the outside, and I'm eroding the cavity from inside for me to enlarge the medullary cavity. And who's going to be breaking down the bone? Can you remind me what is the name of the cell that breaks down the bone? Osteoclasts. Osteoclasts. Also, osteoclasts going to be allowing the bone remodeling, as you see on here, to preserve the shape of the bone. So you don't want to have a growing bone, and let's say you did have an elevation on here, rather than building up another elevation and another one and another one and another one. No, you're going to be breaking down any extra bones that you might get to preserve the same shape of the same appearance of your bones. All right. Questions? All right, moving on to the factors that will be affecting the bone growth. First one is going to be the growth hormone. Growth hormone is a hormone that will be released from a tiny little gland that is pending down from the brain. We call this the pituitary gland. And one of the hormones that will be released from the pituitary gland, it's going to be the growth hormone. And one of its major target organs is going to be your bones. So bones growth is going to be mediated by growth hormone. If a person has low growth hormone, hyposecretion of the growth hormone, this results in dwarfism. If a person has hypersecretion of the human growth hormone, this is going to result in gigantism. So I would become taller, I would become larger in size, gigantism. Other hormones that also participates in affecting the bone growth is going to be the thyroid hormone. And the thyroid hormone deficiency is going to cause a delay in the growth. And if a baby is born with deficiency in the thyroid hormone, he will develop, if untreated, cretinism. And one of the major manifestations of cretinism is delayed growth and short stature. Other factors include the sex hormones. Sex hormones, as we mentioned, would be promoting bone formation. They stimulate the ossification of the epiphyseal plate. Remember, I am boosting up the cartilage formation as well as the replacement of the cartilage by bone, but the ossification is at a faster rate compared to the cartilage formation. Also, in order for me to have a normal bone growth, I will need to have vitamins like vitamin A, C, D, and of course the minerals I need to build up the bone, like the calcium and phosphorus. So if I don't have enough minerals, I don't have the required vitamins for me to be able to build up the bone, this gonna cause the delay in the bone growth and weakening of my bones. Also, another important factor that promotes bone growth is the physical stress. Physical stress will be stimulating bone growth, and you will notice this if an athlete, if you compare the size of your bones to the bones of a person who practice every day, he puts a lot of physical stress on his bones, you will definitely see that his bones are larger than yours. So even if you do have the same body weight, he gonna have larger bones simply because of the physical stress he puts on his skeleton. A very important homeostatic balance I need to keep is going to be the blood calcium level. And remember, I need to have normal blood calcium level in order to maintain normal cardiac function, normal function of the nervous system. So all this is going to need to be maintained by having normal blood calcium levels. What happens if I don't have enough intake of calcium? So I don't drink milk, I don't have any source of calcium coming in for me to maintain this blood calcium levels. This is going to result in a drop in the blood calcium level. And this drop in the blood calcium level going to be detected by 4 tiny little glands that are located in the back of the thyroid gland. We call those tiny little glands, those are the parathyroid glands. Parathyroid glands are going to be releasing a hormone in response to this drop in the blood calcium level called PTH, or parathyroid hormone. PTH, as a result here, going to be, once released, it stimulates the osteoclasts to degrade the bone. And once you degrade the bone, remember what's forming your bone? It's formed of protein, attached to it calcium. So if you break down the protein, what's going to happen to the calcium? The calcium is going to be free and now is capable to travel from your bone to your blood. So this degradation of my bone tissue gonna result in an increase in the blood calcium level, and I do this only to maintain normal blood calcium level, to maintain the homeostatic balance in the calcium. All right, questions? So again, what is the hormone responsible for the activation of the osteoclasts for them to degrade the bone matrix and release the calcium? This is called my parathyroid hormone, or PTH, exactly. Again, what do we call the hormone responsible for the stimulation of the osteoclasts for them to break down the bone? This is my PTH, parathyroid hormone. All right, so I want to discuss the fractures, bone fractures, after we discuss the actual bones first. So we're gonna need to discuss the bones, which is gonna be the main topic of the next lab exam. I want to discuss with you the anatomy part of the skeletal system, which is chapter 7, which is in part of chapter 7. You can see, you can find those diagrams that will contain the important diagrams for the upcoming lab exam under the lab documents on Canvas. So please check those out. You have two files, one for the appendicular skeleton and one for the axial skeleton. So you're gonna see this is the name of the file, APIL 6 axial and APIL 7 appendicular. All right, those are gonna be the PowerPoints for the upcoming lab exam. All right, any questions? Any questions? Any questions? We're gonna discuss the fractures after we complete our discussion of chapter 7. All right. So next class, we're gonna start our discussion of the axial skeleton, appendicular skeleton. I highly recommend